Welcome back from that short ad break. Let's continue with our unpacking of this concept of energy and how it relates to photons and electromagnetic radiation. Let's jump to our concept map to just remind ourselves of what we've said already. So we've been talking about electromagnetic radiation. Whoops, wrong slide. Need to get my pen activated. We've been looking at electromagnetic radiation, and we've unpacked how it behaves like a wave and a particle. We've discussed how it propagates from one place to another. We've linked this idea of a spectrum of electromagnetic radiation to each type of electromagnetic radiation having its own different frequencies. And now, most recently, we've looked at how the frequencies can be related to this concept of energy using the formula E equals HF. Now, before we go further, let's do some practice to make sure that we've understood these ideas and see how they can be used to better understand things that happen to us around electromagnetic radiation on the day-to-day. So this question asks us to explain why a doctor always needs to wear a protective vest when performing an X-ray on a patient. You can see in the photograph down here, doctor, or in this case a vet, wearing a X-ray protecting vest. It's usually got some heavy, dense material like lead in it to prevent the X-rays from getting into them. But we want to understand why they need to wear this protective vest, but you don't need any protection when you use your cell phone. Now, cell phones are a staple of modern life. We see them everywhere we go, and we know very few people who don't use them, at least in part. But a lot of people say that they can be dangerous. They use electromagnetic radiation to transfer signals. So can we use what we know about electromagnetic radiation and its energy to see whether it really is that dangerous to use a cell phone? Let's have a look. So we're being asked to explain why a doctor needs to wear a protective vest when performing an X-ray. Medical X-rays have a wavelength of 10 times 10 to the minus 12 meters. So a very short wavelength, and therefore we know a very high frequency. While on the other hand, commercial microwaves that are used by cellular phones only have a wavelength of 5 decimeters, which is quite a bit bigger than the wavelength of the X-rays. So let's use those values for each of these types of electromagnetic radiation to see how much energy a photon of them would transfer. To do this, we're going to make use of a different version of our original formula for energy, wherein the frequency has been replaced with the speed of light c divided by the wavelength. We obviously got that from our wave equation from the previous lessons. So to find this answer, we're going to need Planck's constant, h, which we've written down, the speed of light, 3 times 10 to the power of 8 meters per second, and then we're going to have to substitute those values along with our wavelength for medical X-rays into the formula to get the answer. To do that, we'd best use a calculator. So our formula is E is equal to hc divided by lambda. So we're going to need a fraction, and into our first bracket we're going to put Planck's constant, 6.63 times 10 to the minus 34, close bracket. And we're going to multiply it by the speed of light, which is 3 times 10 to the power of 8, whoops, I've added too many, times 10 to the power of 8, close brackets. And this all needs to be divided by 10 times 10 to the minus 12 meters, the wavelength. Once we have that, we can push equals, and we get that the energy value is only 1.989 times 10 to the minus 14. 1.989 times 10 to the power of minus 14 joules. Quite a small amount of energy from a single photon of a medical X-ray, hey? But how does this compare to the energy of a cell phone? Let's have a look. So we're still being asked to find the energy here, and we're going to use the same formula as before, but now the wavelength is different because we're examining those of commercial microwaves. They have a wavelength of only 5 decimeters. Now, when we see this decimeter value, we must remember that we're going to need to convert this value into meters. All right? 1 decimeter is 10 centimeters, so 5 decimeters is going to be 0.5 meters. Still quite a large wavelength. So now that we have our numbers, we can start to do a calculation, can't we? Let's go. We're using the same formula again because we do not have the frequency of the cell phone electromagnetic radiation for this particular question. Again, we only have its wavelength. So, just as before, we need to make use of our calculator. Clear the last sum, but the formula is still the same. Need our fraction with Planck's constant, 6.63 times 10 to the minus 34. Once again, multiplied by the speed of light, 3 times 10 to the power of 8. But now, the value is only divided by half a meter. And when we push equals, we can see that our energy reading is 3.978 times 10 to the 25. 3.978 times 10 to the power of minus 25 joules. So would you look at that? The amount of energy a photon of cell phone radiation is carrying is significantly smaller than that of a medical X-ray. So what can we infer from that information? All right, so we have already established that medical X-ray photons have an energy of 1.98 times 10 to the minus 22 joules. And we've just calculated to show that the photons of commercial microwaves, those used by cellular phones, have an energy of only 3.978 times 10 to the minus 25 joules. Once again, an order of more than 1,000 less than those of the X-rays. So it's obvious to us right now that X-ray photons carry a lot more energy and so are able to transfer more energy to the materials that they impact. While in the case of cell phones, the energy is quite low and therefore is not really able to allow the photon to penetrate very deeply into you or me or anything around the cell phone. Let's have a further look though. We can clearly see that medical X-rays have a much higher energy output than commercial microwaves from cellular phones. The photons of commercial microwaves had significantly less energy than even the infrared photons from the fire in the question that we calculated in the previous segment. So, do you still think that cell phones are dangerous, even after we've done all the calculations? Hopefully next time you hear someone tell you that cell phones can cause cancer, that you'll have the information now to tell them they have absolutely no idea what they're talking about. Let's look at another question quickly, this time from an exam, to see what you might be expected to produce. So our question simply says, consider a laser pointer and a cell phone, as shown in the images below. This is a typical laser pointer like used by professors and kids as toys. It just shines a dead straight line from the pointer. And a cell phone we are well versed in. Our first question says, state the type of electromagnetic radiation that is emitted by the laser pointer and the cell phone. So have you used the laser pointer before? I'm sure you've at least seen a cell phone in use before. So which one do you what type of radiation are they each using? Let's have a look. Laser pointers emit red light, which lies in the visible spectrum. And so we know well that red light has a wavelength of 620 nanometers. Our next question of this longer question asks us to define the term photon. Do you remember what a photon is from the previous segments? Can you remember its definition? Remember that you need to know all these definitions as part of your preparation for tests and exams. So let's see what the definition is. A photon is defined simply as a quantum of energy and that is associated with electromagnetic radiation or energy. Remember, a quantum is just a fancy word for a packet of energy that can't get any smaller. So the definition makes a lot of sense that photons are just packets of energy associated with electromagnetic radiation. Let's go further. Part C of this question says, if the laser pointer uses light of wavelength 620 nanometers, we are told that we need to calculate the energy of a single photon of this red light. So how are we going to do it? Just like we've done it in the past, we're going to use our formula E is equal to hc divided by lambda, where h is Planck's constant and c is the speed of light. Let's move straight to the calculation. So in our calculation, we need to substitute our values. But one thing we must make note of is that the wavelength is not in meters and needs to be converted to 620 times 10 to the power of minus 9 meters because it's nanometers. So to do our calculation, we're going to need our calculator. Quickly clear it. Our formula is still the same. We have in brackets 6.63 times 10 to the minus 34 for Planck's constant, multiplied by the speed of light, 3 times 10 to the power of 8, all divided by our new wavelength for red photons, 620 times 10 to the minus 9 meters. Oh, I've made a mistake on the calculator. Let me just fix it. And then we hit equals. And we get that the energy of a photon of red light is only 3.208 times 10 to the power of minus 19. So we can see that the light from a red laser pointer carries quite a small amount of energy. What else does this question ask us to explain or understand? The last part of this question, part D, simply asks us to use our understanding of electromagnetic radiation to explain why it is very dangerous to shine a laser pointer into a person's eye. Now, from our previous calculation, we had shown that there is some energy associated with the photons from the laser pointer. Now, what makes this particularly dangerous is not just that they're going to transfer energy to someone's eye, but also that a laser pointer produces a very narrow beam of light that is full of many, many photons, and so can easily damage the sensitive tissue at the back of someone's eye. So remember, don't ever point a laser pointer at anyone's eyes. Right, that's all we have time for. I hope you've enjoyed all of this unpacking of the concept of energy and electromagnetic radiation.